Hey guys, welcome back to AlgoYogi. We are doing binary search series, and our next problem in the list is find minimum in rotated sorted array. Okay, so let's go to LeetCode. Suppose an array of length n sorted in ascending order in rotated between 1 and n times. For example, the array basically from 0 to 7, 3 missing, might become this if it was rotated 4 times. What does 4 time rotating some array mean? So if this was the array, then we're gonna take values one by one 4 times from back of the array to the front. So if you take 7, I'm gonna show it on example, but let's read what it is asking us. So after rotating 4 times, this becomes this array, this original array becomes this, and after rotating 7 times, which is also the length of this array, this becomes exactly same. Okay, if you rotate something that same number of time as its length, then it will become same. So in rotation, what we are doing is we're sending the number one element from the back of the array to the front, right? So first time we sent 7, second 6, third 5th, fourth. So if you see here, 4 times rotation done, 4 is in the beginning, 5, 6, 7, and then whatever was remained over here, in the beginning. And if it was rotated 7 times, so which means 3 more times from here, it will become this. So what we need to do is we understood like this rotation part. Given the rotated array nums of unique elements, these are unique elements, return the minimum element of this array. And you must write the algorithm that runs in big of n time. So if you see, this is the array that's given to us. And we know it's rotated some number of times. We are not told that how many number of times it's rotated. If that was given, we will immediately go to basically that particular element. If let's say it was rotated like 3 times, 4 times, or whatsoever, like let's say it was rotated 3 times, that means we will go to the third index, and then whatever is the number right next to it, if it has, then we will basically return that, because that would be the minimum, because first part was rotated. This first 3 values come from the back of the array. What I really mean is, initially this array must have been 1, 2, 3, 4, and 5. Right, this was the array. Then it was rotated first time, that must have made it 5, 1, 2, 3, and 4. First rotation. Then second rotation would make this as 4, 5, 1, 2, and 3. And then third rotation will make it basically 3, 4, 5, and 1 and 2. And this is the array that's given to us over here, right? This is the array that's given to us over here. Just gonna minimize it a little to show you guys. So this is the rotation that we're talking about, but that's not our focus. Our focus is to basically find the minimum in this rotated array. This array is sorted and it's also rotated, so we can absolutely find the minimum element by doing a linear search, which will be of big of n time complexity. That's so easy, right? But that's not the right solution, because we have been asked to give us a solution that is of time complexity big of log n. So how to apply binary search, because most of the time this time complexity is achieved with binary search. Okay, because we are in binary search, we are able to bring down our input size each time in each basically step by half. So we know that in this particular array, what we need to do is apply binary search. So what we will really be doing is we'll have left and right pointers. That's basically the core of binary search. So here we have left and here we have right. right both on the edges. Now we need to find the minimum element between this sorted rotated array or rotated sorted array. Okay, what I really mean is this should have been sorted rotated array, because it was sorted first and then rotated. Okay, so if it was rotated first and then sorted, it would be a really sorted array. They should change the definition. I'm really sure about that. Okay, now how about we find the mid here? So let's find the mid here. So how do we find the mid? Mid is basically left plus right minus left divided by 2. So just to avoid the overflow, in this case, for the first time we are finding the mid. If we write the index here 0 1 2 3, I'm just gonna step by step run it on this first example, and just also write the pseudocode here. So what's really going to happen here is first mid would be 0 plus 4 minus 0 divided by 2 would be 2. So this is my mid for now. So if my nums mid, the whole thing here is like we need to compare, because we know that the number that we just chose, it could fall into one of the sorted part. It could be the first sorted part. In this case, if you see, this is one sorted part, and although this m didn't have to lie here, m could have been just 4 as well, then also this mid is part of this sorted part. And next is this is another sorted part, because after rotation what must have happened is some sorted elements just went in the front of the array, so which basically divided this one sorted array after rotation into two sorted array. And that's the trick that we will be playing here to find this minimum element. So if my mid element that I just found, this mid is greater than my right, that means what? This can never be my minimum element. So what do I do? If this cannot be my minimum element, I need to basically move my left pointer to mid plus 1. Okay, I need to search now in the basically right portion, and that's because when I found this mid element and I'm checking it, if it is greater than my right element, that means the lowest point would be basically in between these two pointers, like m plus 1 and right pointer. So I'll move my left pointer to mid plus 1. Okay, mid plus 1. Let me take this over here. Okay, yes. Now what I'll do is this left pointer from here, since we are doing basically a run, so what I'll do is I'll move this left pointer to basically over here. Okay, this mid is gone, my left pointer is now over here. So what happens now? We'll again calculate the mid. So in this case, what will happen is our mid will be 1. Our mid will be 1, right? L plus r minus basically 4 minus 1 divided by 2 is basically nothing, so that will be just 3 is my mid now. So what is the element over there? Like, is this mid? This is my new mid now. Is this mid greater than my right pointer? Is it? It's not. So there will be an else case here, right? There will be an else case here. So what do we do in else case? What are we going to do in else case? We will move our right pointer to basically mid minus 1, but we shouldn't, because this could be a potential answer. Right? Since there might be a case where there is no element before it, and this could be the smallest, so I'll keep this as r equals to mid so that I don't miss this element, right? So now what do we do? I will again now my right is mid here, so I'll move my right over here. This right is gone. I will run the loop again. So in next case what will happen is I will calculate this again, and that same situation will occur. Left and right pointing to 3, mid will be 3, which is 1, else case r again becomes this. Left does not change its position. So it will be basically an infinite loop. If you see this will be an infinite loop. We'll be stuck over here. So what we really need to do is, since we know we reached my minimum element here when I was placing my right pointer to mid, so I will have my condition while instead of L greater than R, I will just have keep processing until my left pointer is smaller than R, not equal to, okay, no equals to this time. That's when what will keep happening is I can just return my R as my mid element. So I will just return mid, or not mid, sorry, my bad, this R as my upper bound, and which will be the answer. Okay, first we made the decision if the mid that I'm choosing is greater than basically my right. If it is greater than my right, then I need to basically go to the right side, and if this is not true, that means I need to bring my right to mid so that I can search in the first half now. Okay, in the first half. All right, I mean, if this was smaller than this element, this we need to understand. If let's say if this was supposed to be smaller than this, which is this else case, then I know in between these elements this must have incremented, right? This must have incremented, gone up, because this is part of basically some sorted array, so it must have incremented, right? But in this case we know that there must be some downfall because this is not greater than 2, and 2 must have some element that's lesser than 2 that potentially is our minimum element. So that's why we are basically choosing R, moving R to basically L to next, m plus 1, and R to basically m. If this was greater, let's say it was 8, that must have been, the values must be 6 or something like that. Okay, so let's write down. It will be easy implementation. Okay, I think these problems can become a little complicated, at some point, because once you keep like just comparing them, there are multiple versions that exist. You could maintain like a result variable, and you could still have the condition where left is smaller than or equals to R, and then keep when you find that element, keep comparing it with the last, both sides, and keep moving, because what you're really trying to find is this side that you need to go. Okay, in this case we were able to choose, and this is, I guess, like the easiest solution of all. So we'll have left and right pointers pointing to 0 and length nums -1. While left is smaller than right, let's find mid. Mid is basically left plus right minus left divided by 2. Okay, I will still just place it just to be safe in here. So if nums mid is greater than nums R, that means our answer will exist in basically mid plus 1 left side, right side. Otherwise, else case would be move your R pointer to just mid and return mid. Okay, let's zoom out and run it. Okay, and yup, we must have done something wrong. So we're not returning M, we are returning R, and not just R, we are returning the index or the number. I think we're returning the number, so let's return nums at r. Okay, now it will be okay. All right, and voila, let's submit it. Time complexity would be whatever was asked to us, log n. Space is nothing, which means constant, because we're just playing around with the pointers. So space would be big of 1. Alright, okay, we're done here. Let's go to AlgoYogi, mark this solved, and see you guys later in the next problem. Until then, bye bye.